This presentation will introduce characterized resources in Stroboscope. In the past, we examined this Earthmoving model in EasyStrobe that uses two kinds of haulers to move the Earth from the Q soil to move to the Q soil in place. This model uses 10 cubic yard haulers as well as 20 cubic yard haulers. In EasyStrobe, this requires that we model the cycles for each size of hauler separately. As we shall see in Stroboscope, that is not necessary. The Stroboscope model shown here is much simpler. There is only one cycle of activities for the haulers, which includes the combi load, the normal haul, the normal dump, the normal return, and the Q hauler queue. Both types of haulers will flow through these nodes. In addition, this model has queues that hold characterized resources, such as a loader queue and hauler queue. Loader queue holds one loader, which in this case is a shovel. Hauler queue holds two kinds of resources, two big haulers and three small haulers. The definition of resources is shown here. The first resource is a generic resource, which is defined by the statement gentype soil. The second resource is a car type resource, which is a characterized type, whose name is loader. The identifiers that follow, size, P5, M, and P95, define the properties of the characterized resource of type loader. Notice that we cannot initialize a queue directly with resources of type loader. Instead, we must define subtypes of the characterized type loader, and we can initialize queues with those subtypes. In this case, we define a subtype of the type loader, which we call shovel. The shovel has specific properties that are shown by the numbers that follow. Its size is 5, its P5 is 0.5, the mode M is 1, and P95 is 1. The next characterized type defined is hauler. This particular characterized type only has one property called size. The next two statements, subtype, define two subtypes of hauler. The first one is called big hauler, and the second one is called small hauler. And they also define the numeric values for the property size. The big hauler has a size of 20, which implies cubic yards, and the small hauler has a size of 10, again in cubic yards. The Q hauler queue holds resources of characterized type hauler. Before simulation starts, the Q hauler queue is initialized with two big haulers and three small haulers. This is accomplished with the statements shown here. Init hauler queue 2 big hauler, init hauler queue 3 small hauler. What these two statements do is to insert into hauler queue two big haulers, which are in the front of the queue, followed by three small haulers, which are in the back of the queue. So what we end up with is a real queue with individually identifiable resources, in this case 5 resources, where the first two in the front of the queue are big haulers, and the last 3 in the back of the queue are small haulers. The Q loader queue is initialized to haul one shovel. The statement that does this is init loader queue 1 shovel. Notice that in all init statements, we have to specify the name of the queue followed by a number followed by the subtype that we want to create and insert into the queue. The only other resource involved in this network is the generic type soil, which is used to initialize the soil to move queue with 15,000 cubic yards of soil. There is only one combi in this particular model. At the start of simulation, Stroboscope will examine combi load to see if it can start. This is determined by examining the enough attributes of the three incoming links into combi activity load. In this case, links LD1, SL1, and HL1. If the enough attribute for all three links LD1, SL1, and HL1 is true, then activity load will be able to create an instance. After an instance is created, activity load will have to start a drawing process through the three incoming links. The order in which the three links LD1, SL1, and HL1 are defined is very important at this point. The numbers in parentheses 1, 2, and 3 indicate the order in which these links have to be defined for the drawing process to actually work as intended. In this case, LD1 and HL1 can be defined either as the first or the second link, but the important thing is that link SL1 must be defined last. It must be the third link to be defined. The reason for this will become apparent in just a moment. Let us assume that link LD1 is defined first. If that is the case, then the new instance of activity load will ask link LD1 to draw resources from the preceding queue. In this case, link LD1 will take one shovel from the preceding queue and transfer it to the new instance of load. After that, the new instance of activity load will ask link HL1 to draw resources from the preceding queue. Link HL1 will then take one of the big haulers, the one in the front of the queue, and transfer it from hauler queue to the new instance of activity load. After that, link SL1 will draw resources from soil to move queue and transfer them into the new instance of activity load. It is at this point that the order of defining the links matters. To see how, let us concentrate on the three statements that control the drawing process through link SL1. The first statement, draw until SL1, makes sure that we draw enough cubic yards of soil to exceed the size of the hauler in the starting instance of load. This is accomplished by comparing the count of the soil in load to make sure that it's greater or equal to the size of the hauler in load. For this statement to make sense, the size of the hauler in load must be something that can be computed, which means that at this point, the instance of load must contain a hauler so we can access its particular size. In this case, the very first hauler will have a size of 20 cubic yards, and it will require that we draw enough soil in the count of soil in load to be greater than or equal to 20 cubic yards. Now, given that the capacity of the shovel is 5 cubic yards, this means that the draw until will have to allow 4 draws to take place. Each one of the draws is determined by the statement draw amount SL1, which requires that we have access to the size of the loader in load. Again, for this statement to make sense, there must be a loader in the instance of load that is currently starting, so we can actually look at its property size and determine that the size of the loader in load is 5 for 5 cubic yards. Each time SL1 draws will then transfer 5 cubic yards from the preceding soil queue to the new instance of load. In addition, SL1 will also sample a new draw duration based on the formula in the statement draw duration SL1. The formula in that statement is simply a random number from the distribution PERT PG, whose attributes are the properties of the loader in load. As a result, every time SL1 draws 5 cubic yards from the preceding soil Q, it will also sample the duration of how long that particular draw of 5 cubic yards took in minutes. The drawing process will continue 4 times. 4 times 5 cubic yards is 20 cubic yards, which is the size of the hauler in low. When the drawing process is complete, then the new instance of activity load will determine its duration. The formula that determines the duration for activity load is SL1.sum draw duration. That formula returns the sum of the 4 random variables that were sampled by link SL1 each time it drew 5 cubic yards from the preceding Q. No other activity can start until the first instance of activity load terminates. When that instance terminates, it will return the loader through link LD2 to loader Q, and it will also create an instance of activity haul to which it will pass the hauler that was in the instance of activity load through link HL2 and the soil that was in the instance of activity load through link SL2. The end result is that the new instance of activity haul will contain a hauler, and it will also contain the amount of soil that it carries. Specifically, for the first instance of activity haul, it will contain one big hauler and 20 cubic yards of soil. When activity haul ends, it will create an instance of activity dump, and it will pass to it the truck, the big hauler that it hauls, along with the 20 cubic yards of soil through the links HL3 and SL3. When activity dump ends, it will transfer the soil to the Q soil moved through SL4. So dump will transfer 20 cubic yards of soil to soil moved. Dump will also transfer the big hauler that it held through link HL4 to a new instance of activity return. At the end of that new instance of activity return, link HL5 will transfer the hauler, in this case a big hauler, to the Q hauler Q. That big hauler that enters the Q hauler Q will go to the back of the Q and join the rest of the haulers that are already there, if any. This means that the haulers will be loaded in the order in which they were placed in hauler Q. First, the first big hauler, then the second big hauler, then the first small hauler, then the middle small hauler, and then last, the third small hauler. The next hauler to be served will be the big hauler that has made the entire cycle through the activities load, haul, dump, and return, and has rejoined the hauler queue. And this process will continue successively for the other haulers. It is possible that haulers might actually change in their respective order, depending on whether some of them had faster haul, dump, or return times and overtook another hauler in the process. Queues have a property called discipline, which we can change by using the discipline statement. Shown here is a discipline statement applied to the queue hauler queue that arranges haulers according to their size. Haulers in hauler queue can be arranged according to one of their properties. In this example, they're arranged according to size. The formula minus size means that when a big hauler enters the queue hauler queue, it will be positioned in front of any small haulers already in the queue, but behind any other big hauler that is already in queue. Discipline arranges resources, giving priority to those whose property is smallest. In this case, minus size will produce a number that is smallest for the large haulers, the big haulers in this case, because their size will be minus 20 and it will be smaller than the minus size of the small haulers, which will be minus 10. The statement release amount SL4 shows how we can model a 10% soil loss in the process. This is accomplished by multiplying the size of the hauler in dump by 0.9 and releasing through link SL4 that amount of soil into soil moved. For this to work, however, it is necessary that link SL4 be defined first before link HL4, so that a terminating instance of activity dump will release first the soil through SL4 before it releases the hauler through link HL4. This is necessary so that we can access the size of the hauler in dump when we release soil through link SL4. If the hauler is released first, in other words, if the link HL4 is defined first, then a terminating instance of dump will release a hauler through HL4 to a new instance of return, and then when we try to release the soil through link SL4, we will try to access the size of the hauler in dump, and there will be no hauler in dump, and Stroboscope will give us an error message. Getting the order of links wrong is a very common error that students make when they're first learning Stroboscope. This example actually has two networks in it. On the upper right corner, there is a second network that represents a clock, a daily clock. This network has one combi, work AM, which represents the work in the morning. It is succeeded by a normal activity lunch, which represents a 1 hour break for lunch, which is succeeded by work PM, which represents the work in the afternoon, which is succeeded by off shift, which represents the time from the end of work on one day to the beginning of the work on the next day. The clock begins by initializing the queue start with one unit of resource. The unit of resource in this case is called CH, which stands for clock heart. It is just an artificial resource to make the clock work. There are two things to notice about this network. The first is that this subnetwork works continuously. It cannot stop. And as a result, the simulation model must have a stopping condition based on time, as opposed to expecting the simulation to end when soil to move queue becomes empty. The second thing to observe is that the subnetwork for the clock and the subnetwork for the earth-moving operation do not have any links in common. They're completely independent and they run in parallel while the simulation is running. To control when activities can actually take place, we define a variable called work time, whose formula is workam.carinst or workpm.carinst. This is a logical formula that returns true if there is an instance of work AM going on, or if there is an instance of work PM going on. Notice that at any given point in time, there can be at most one instance of each of the activities of the clock. So the carinst of work AM can only have the values 0 or 1, and the carinst of work PM can only have the values 0 or 1. So when you take a logical OR between the two values that are 0 or 1, the result is either 0 or 1, depending on whether work AM has an instance or work PM has an instance, in which case work time is true. We can take advantage of this variable work time by defining a semaphore for the combi activity load. A semaphore is an attribute of a combi activity that is examined even before the incoming links are examined to see if they have enough resources to support a new instance of the activity. So the very first thing that is examined before we start a new instance of activity load is to see if the semaphore of activity load has the value true. The default value for a semaphore is true. We can change it using the semaphore command as shown here, semaphore load work time, where work time is a logical variable that returns the value true or false. Clearly, the semaphore for activity load will be true only during work time, and that will allow a new instance of activity load to take place, i.e. to start, only when the variable work time returns true. The end effect is that activity load can only start when the clock has an instance of work AM or an instance of work PM. The other activities, hold, dump, and return, are normal activities. They do not have a semaphore, and if they have started, they will continue and finish the cycle so that all haulers will return back to the hauler queue before they get stopped, because they cannot start an activity load, because activity load is stopped by its own semaphore. The next page shows the stroboscope input file for the model that was presented on the previous page. The model begins by defining a seed for this particular model, and then it follows with a display statement that will display in the output the message. Notice that this display statement takes several lines in the input file and continues until it reaches a semicolon. We then have 4 variable statements that define the variables NBH, number of big haulers, SNH, number of small haulers, NL, number of loaders, and amount of earth to move, 1500 cubic yards. After that, we have another display statement that essentially reproduces the input that was used for this model. After the display statement, we have 5 more variables. The first one is the days to simulate, which is 5, the day length, which is 1,440 minutes per day, the AM shift length, which is 240 minutes, which is 4 hours, the PM shift length, which is also 240 minutes, another 4 hours, and the break for lunch, which is defined as break length 60, which is 1 hour. After the definition of these variables, we have the definition of resource types. The first resource type is generic, and it's called clock heart. It is the resource that is used to make the clock work. After that, we have the definition of car type hauler. This is the characterized type for hauler, as we saw before, which has a single property called size. After that, we have the definition of the subtypes of the characterized type hauler. The first subtype is called big hauler, and it has a size equal to 20 cubic yards. And the second subtype is called small hauler, and it has a size of 10 cubic yards. After that, we have the car type loader that has properties called size, P5, M, and P95. The subtype of loader is called shovel and has specific numeric values for size, P5, M, and P95, which are 5, 0.51, and 2. And after that, we have the definition of the generic type soil. Next come the definitions of the network nodes. After the definition of nodes, we have the definition of network links. Again, these are easy to understand, and they simply reproduce the information that is shown on the network. Then come the definition of global variables that are useful for accomplishing other tasks. The first variable is called work time, and it represents a logical value that indicates whether it is now working time or not. The second variable, total working hour, is given by a formula which is the total instances of work in the morning times the 4 hours of work in the morning plus the total instances of work in the afternoon times the 4 hours of work in the afternoon. The entire parenthesis will give us the total working time in minutes, so we have to divide by 60 to turn it into total working hours. We then have the definitions of priorities and durations for the activities that comprise the clock. The work AM activity, which is the only combi in the clock, is given a very high priority, in this case 1,000, so it is the first activity to start and regulate the rest of the activities in both subnetworks. The duration of work AM is AM shift length, which is 240 minutes or 4 hours. After that, we have the duration of lunch, which is break length, which is 60 minutes or 1 hour. After that, we have the duration of work PM, which is 240 minutes again, or 4 hours. And finally, we have the duration of off shift, which is calculated based on day length, which is 1,440 minutes, minus 240 minutes for the morning shift, minus 240 minutes for the afternoon shift, minus 60 minutes for the lunch break. Whatever remains is the duration of off shift. Then come statements related to the subnetwork that models the Earth-moving operations. The first statement defines the discipline of the queue hauler Q, and it has the formula minus size, which allows the big haulers to go to the front of the queue behind the other big haulers, but in front of the smaller haulers. We then have statements that control the startup of activity load. The first one defines the semaphore for activity load to be work time. The second one is the draw until for link SL1, the draw amount for link SL1, the draw duration for link SL1, and the duration of load, which is SL1 dot sum draw durations. All of these have already been described on the network. After that, we have the duration of activity haul, which is given by a normal distribution with a mean of 8 and a standard deviation of 2. The duration of dump is deterministic and has the value 1. And the duration of return is normal with a mean of 6 and a standard deviation. The model is now completely defined, and it is time for control statements. We need to initialize the queues, run the simulation, and present the results. The initialization of queues is done with the init statements shown here. The first statement initializes the start queue with 1 clock heart. The second statement initializes the loader queue with number of loaders shovel. In this case, the number of loaders is simply 1. Then we have the initialization of hauler queue with NBH big haulers. NBH has the value 2, so we put 2 big haulers in hauler queue. After that, we initialize hauler queue with NSH small haulers. In this case, NSH has the value 3, so we put 3 small haulers in the hauler queue. Notice that hauler queue is initialized twice, first with big haulers and then with small haulers, and that is what makes big haulers go to the front of the queue and small haulers to the back of the queue if there was no discipline for the hauler queue. Because there is a discipline for the hauler queue, even if we initialized hauler queue in the opposite order, the big haulers would still go to the front of the queue. Finally, we have the initialization of soil to move with amount of earth to move soil, which is 15,000 units. On the last page, we have again a seed statement, which is redundant in this particular example, followed by simulate until, which is the statement that actually starts the simulation and controls when the simulation will end. This simulation will end when the current count of the queue soil moved is greater than or equal to the amount of earth to move. In other words, when the entire amount of soil has been moved. This does not mean that all the haulers have returned to the hauler queue. They could still be in activities between dumping and returning to hauler queue. After that, we have display statements that display the final results. The results displayed are the total simulated time, the total work time, which is clearly less than simulated time, the apparent production, which is the amount of soil moved divided by total simulated time, and the true production, which is the total amount of soil moved divided by the total work hours. The last statement is the report statement that asks Stroboscope to print the standard report. This page shows the printout from the Stroboscope output when we run the model shown on the previous page. The first line describes the model and gives us information about its characteristics. Then the next 4 lines repeat the input that was used to produce this output. The discipline for the hauler queue is to allow the big haulers to load first. After that, we have display statements that show the output of simulation. After that comes the standard stroboscope report. The sections about queues and activities are very similar to those when we used generic resources. What is new are the sections that follow that give us statistical information about characterized types and their subtypes. The section about characterized types gives us information about the characterized types hauler and loader as classes of resources without distinguishing between big haulers and small haulers. The column carp pp gives us the current population of haulers, which is 5, with 2 big haulers and 3 small haulers, the total population that ever existed, the average population, the standard deviation of the population, the minimum population, and the maximum population. After that, we have statistical information about life, but because none of the resources were destroyed, these entries are blank. After that, we have information about subtypes. We have 3 subtypes in this model: big hauler, shovel, and small hauler. They are listed alphabetically, and that is why big hauler is followed by shovel, which is followed by small hauler. The information that we have about subtypes is similar to the information we have about characterized type. The next section gives us information about the residence times of resources into the various nodes where resources spend time. Resources are called customers here, and the nodes where resources spend time are called hotels. The analogy is useful for understanding the concepts that follow. Resources are like customers that visit hotels and spend time there. The column average entries shows the average entries that a big hauler, let's say, made into an instance of dump. The next column shows the average total time that a big hauler spent in an instance of dump. The next column shows the average visit time that a big hauler spent in an instance of dump. This is easy to understand because the duration of activity dump is deterministic, it is 1, so a big hauler on average spends 1 minute in an instance of dump. After that, we have the standard deviation, which is 0 because the duration of dump is deterministic, and the minimum and the maximum visit times are both 1s, again, because the duration of activity dump is deterministic. Now, we could contrast this to the next line that shows statistics about the residence of resources of type big hauler in instances of activity haul. Again, there were 216 average entries where the resources spent a total of an average total time of 1,770 minutes, where the average visit time was about 8 minutes. If we divide 1770 by 216, we do get 8 minutes, 0.20. Because the duration of activity haul is probabilistic, we have information about the standard deviation of the average visit time, the minimum of the visit time, and the maximum of visit time, which of course are different numbers because of the duration of haul is probabilistic. After that, we have information about the future events list that shows all the instances of activities that are still going on. And then after that, we have some information about the run of the stroboscope model. The first model, for example B2, allows any number of haulers to dump at the same time. Because of this, it is possible to allow soil to flow through the network through the links SL1, SL2, and SL3 and SL4. If we need to introduce a spotter so that only one truck can dump at the same time, then it is not easy to model the flow of soil through the network. The second model, for example B2, allows only one hauler to dump at the same time. It is as if though we only have one spotter, in which case the soil does not flow through the network, but is instead created by link SL4. Notice that all the soil links from activity load to activity dump have been removed. Only the soil links SL1 and SL4 remain. Also notice that even though only one truck can dump at the same time, there is no queue for the spotters. To prevent activity dump to have two instances at the same time, we introduce a semaphore, which is shown here. Semaphore dump not dump.carInst. The variable dump.carInst gives us the number of current instances of activity dump, which in this model can only have the values 0 or 1. It is 0 if dump does not have any current instances, and it is 1 if there is one instance of activity dump going on. Putting a logical not operator in front of either a 0 or a 1 will return the value 1 or 0 depending on the case. So if there are no current instances, not 0 will give us the value 1, which is true, so the semaphore for activity dump will be true, and activity dump might be able to start if there is a hauler in the queue wait to dump. On the other hand, if there is an instance of dump going on, then dump.carInst will be 1, in which case the logical not of 1 is 0, which means that the semaphore for activity dump is false, which means that no other instance of activity dump can be created. So this logical statement ensures that at most only one instance of activity dump may exist at any given point in time, which is the equivalent of having just one spotter. As indicated in the comments, this modeling approach is not recommended because it hides the logic and does not provide the spotter queue statistics that we would get by actually having a spotter queue. Since activity dump does not receive any soil resources, the link SL4 that carries soil resources must create those soil resources and then transfer them into soil moved. This is accomplished by having the statement release amount SL4 with the argument dump.hauler.size, which returns the size of the hauler in the instance of activity dump that is about to terminate. As shown in the notes, Stroboscope will give a runtime error when it evaluates the above expression, i.e. dump.hauler.size, if link SL4 is not defined before link HL5. To avoid this common error, open the dialog box for combi dump and make sure that link SL4 is defined before link HL5. This ensures that dump will release first the soil through link SL4 and then the hauler through link HL5, i.e. the hauler must still be inside the terminating instance of dump for the variable dump.hauler.size to make sense. The remainder of the model is identical to the first version of the model presented earlier. This page shows the simulation output for the second model for the example B2. The results in this output file are very similar to those for the first model. It is interesting to notice that the total simulation time for the second model is about 7 minutes less than the simulation time for the first model. The true production for both models is exactly the same, at 208.33 cubic yards per hour. This shows that the addition of a spotter does not make any difference in this model, which implies that we do not have enough haulers in the system so that they would actually create a queue at the dump location. This is also indicated by the average weight and the average contents of the queue weight to dump, which are very small at 8% and 1% respectively. The third model, for example B2, is shown on this page. In the third model, the amount of soil loaded into each hauler is a random variable. As a result, we need to construct a mechanism by which each hauler will know exactly how much soil it was loaded into that hauler so that it will dump exactly that amount of soil into the queue soil moved. This model also has a restriction that only one truck can dump at the same time and uses the queue spotters to accomplish this task. The queue spotters is initialized with one spotter. The mechanism by which each truck knows exactly how much soil was loaded into it is by using saveprops. Saveprops is a new type of property that we need to describe for this particular model. Notice that the network itself does not tell us the details about how this model actually works. To understand how this model works, we have to look at the actual stroboscope statements. The important stroboscope statements are summarized here. The first statement is saveprop, which takes as an argument the name of a characterized resource, in this case hauler, and then defines a new property called soil loaded. This property is different from the ordinary properties because we can store numbers in that particular property. It is like having a pocket that each hauler carries with it, and within that pocket it saves a particular number which we access by referencing the property soil loaded. The next statement, varprop, takes as an argument again the name of a characterized resource, hauler, and then defines a property called overload. This property is different from a saveprop in that a varprop is actually a formula that operates on the properties of a hauler. In this case, it subtracts size from soil loaded. Soil loaded is a saveprop, whereas size is an actual property of hauler. The next statement, varprop, takes again as an argument the name of a characterized resource, in this case loader, and defines a new property called bucket dur, which refers to the formula PERT PG. This formula represents the duration of how long it takes for a bucket to dump into a hauler. To see how the amount of soil loaded into each hauler is a random variable, let us concentrate on the three statements for link SL1: draw until, draw amount, and draw duration. The draw until statement for link SL1 specifies that we should continue drawing until the count of the soil in load, that is, the amount of soil drawn, is greater than or equal than 90% of the size of the hauler in load. The statement draw amount SL1 specifies that the amount that is drawn every time that we draw through link SL1 is the size of the loader in load multiplied by a uniform random number between 85% and 105%, which implies that each scoop that is deposited into the truck is a little bit more or a little bit less than the nominal size of the scoop of the loader. Because the amount loaded into the scoop of the loader is variable because of the uniform random number, it is not clear how much soil is placed into the truck every time we draw through link SL1, and it is not clear how much soil will actually go into the hauler at the end of the drawing process. The drawing process will occur many times and will continue until the draw until becomes true, that is, until the amount of soil that has been drawn into the current instance of load exceeds 90% of the capacity of the hauler in load. Again, it is uncertain how many draws this will require. Every time link SL1 draws soil from the preceding queue and deposits it into the new instance of activity load, it also samples the result of the expression load.loader.bucketDoer. BucketDoer is a type of property of the loader that is currently in load, but it is not an ordinary property. It is not a static number. Instead, BucketDoer is a varprop which returns a random number from the PERT PG distribution that takes as argument the P5, the mode, and the P95 of the loader. Notice that P5, M, and P95 are static properties of the loader. They are actually numbers associated with the subtype shovel. Even though we know that the numbers will come from the subtype shovel, the formula for the varprop refers to the type loader because it is general. We could have two types of loaders, in which case the varprop should apply to both. As before, the duration of load is SL1.SUMDrawDuration, which will give us the sum of the random numbers that were sampled every time link SL1 drew from the preceding queue that contains soil. The next statement on start introduces the concept of an action event. This event will take place on the start of activity load. What exactly will take place depends on the arguments that follow. In this case, we assign to the saveprop load.hauler.soil_loaded the result of load.soil.count. In simple language, what we do is to store into the saveprop soil loaded of the hauler that is actually inside the current instance of load the count, that is the amount of soil that is currently in the instance of load. And this will occur on start of activity load, that is after all the drawing through link SL1 has finished and we know exactly how much soil is in the instance of load. That amount of soil is given by load.soil.count. That was the amount of soil drawn, and that is the number that will be stored in the saveprop soil loaded of the hauler in load. Each hauler carries with it that saveprop soil loaded that contains the number which represents the amount of soil loaded into that hauler. At the end of activity dump, we release through link SL4 an amount equal to dump.hauler.soil_loaded. In other words, an amount equal to the soil loaded in the hauler that is currently in the terminating instance of activity dump. Notice that for this variable to make sense, that is dump.hauler.soil_loaded, it is necessary that link SL4 be defined first and link HL5 be defined after that, so that activity dump, when it terminates, it releases first the soil through SL4, which refers to the property of the hauler inside the terminating activity dump, and then activity dump may release the hauler through link HL5 to a new instance of activity return. The statements up to here are enough to define the complete model. The remaining three statements illustrate how to define a statistics collector and how to collect numerical values into that statistics collector so that we get the output that we desire. In this case, the statement collector defines a collector called overload per hauler, which will give us statistics as to the amount of soil that is loaded into a hauler above and beyond the hauler's capacity. The next two statements illustrate how to actually collect values and store them into that statistics collector. Notice that they are both alternatives, so we must use one or the other, not both. The first statement, on release HL2, collects into overload per hauler, which is the collector, the result of the expression overload. And overload is a varprop defined for the resource hauler that has the formula soil loaded minus size, which is positive if the amount of soil loaded exceeds the size of the truck. Notice that because this statement occurs on release through HL2, the link HL2 contains only one hauler at that point in time, so it is evident as to which hauler we want to access when we access the property overload. The next statement, before end, occurs at the end of activity load, and the action is very similar to the previous statement. Again, we collect into overload per hauler, but this time we have to specific as to what it is we want to collect. The correct variable is load.hauler.overload because now overload is a property of the hauler which is inside load, and activity is a multi-receiver. So activity load can hold several resources of different types. So we cannot access the property of any one of those resources without specifying which resource it is that we want to access. In this case, the variable load.hauler.overload makes it clear that we want to access the property overload of the hauler in load and not of any other resource. This is the output file for the third model, for example B2. It is very similar to the output for the previous models. Notice that the total simulated time is a little bit more than the previous models, and that the true production of the system, 197 cubic yards per hour, has dropped from 208 cubic yards per hour. So it is about 11 cubic yards per hour less. The reason for this is that most of the time the haulers are not filled to capacity because the draw and till allows them to be filled up to 90% or more of their capacity. All sections for this output are very similar to those for the previous models. What is new is the section about collectors, which lists the new collector that we have defined called overload per hauler. Notice that we have collected 1,087 samples, which means that activity load occurred 1,087 times, and that the mean value is negative 0.3. This means that, on average, trucks were not loaded up to their capacity, but instead they had 0.3 cubic yards less than their capacity. The fact that the average is negative, however, does not mean that there were no trucks that were overloaded. This is shown by the minimum and the maximum values. On the minimum side, there was a truck that carried 1.97 cubic yards less than its capacity, and on the maximum side, we see that there was at least one truck that carried 4.17 cubic yards more than its capacity. Nevertheless, on average, trucks carried less than their capacity, and that is why production is less in this model.